Okay, let's have a quick look at the contents of Chapter 1. Chapter 1 contains a discussion about the scientific method, what science really is. I put a little video up on YouTube some time ago about what the scientific method is and what's a good observation and why people are unreliable. That's already up there on the YouTube channel, and the link is in Blackboard. So we're just going to skip down through that. These are the testable parts. Okay. The scientific method part's not really going to come up so much on the quizzes. This part right here. So we need to talk about if chemistry is the scientific study of matter, and matter is something that exists and can be measured, we have to talk about units of measurement. And we're going to be in the metric scale, and we're going to use scientific notation to make the very small numbers and very large numbers be easier to handle. And then, well, we're going to have to do something with those numbers. We're going to have to combine them or do calculations with them. And inherent with every number is a degree of precision. And that precision shows up in something called significant figures. And whether we're doing a multiplication or an addition, we treat those significant figures a different way. Okay, so let's talk about units of measurement then. In science, we have things that are called fundamental units. These are units of measurement that describe things that exist in their own right and that they cannot be described as combinations of other things. And those are mass, length, time, energy, and temperature. These are our fundamental units. These are all metric. The mass unit is measured in grams. That's given as a lowercase g. Length is measured in meters, which is a lowercase m. Time is measured in seconds, because all other measurements of time, like minutes and hours, are not decimal. And non-decimal numbers are just a non-starter in science. Energy is measured in joules. There is a beautiful little measurement of energy called the calorie that we might come back and visit at the very, very end. But our official unit of energy is the joule. And temperature is measured in Kelvin. Kelvin can be described in terms of Celsius, because the Kelvin scale and the Celsius scale move hand in hand. Never, ever, ever, never, ever are we allowed to mention the other temperature scale. Kelvin is the official scale. Celsius is a nice scale because it describes everything that we understand between 0 being water freezing and 100 being water boiling. If you've heard of another temperature scale, it's not used in science at all. So we're not going to even mention it. Okay, now, all of our units break down exactly the same way. We're going to talk about our units in increments of 1,000. So if I were to talk about mass, here's a gram. If I multiply that gram by 1,000, going up 1,000 is making a kilo. I've just generated a kilogram. And a kilogram is 1,000 grams. And that number and this number, its scientific notation equivalent, don't really seem to be any different. We'll come back to that in a second. If I take my kilogram and I multiply that up by 1,000, just realized I didn't put 1,000 in there. Then I make a megagram. No one really says megagram. But that would be 1,000 thousandths, so that would be 1,000,000 grams. If I take my gram and I divide it into 1,000 equal pieces, that prefix is now milli. I just made a milligram, and a milligram is 1,000th of a gram. And the scientific notation is 1 times 10 to the negative 3. Now the scientific notation works this way. Count the number of zeros. There are 3 zeros in the number 1,000, and the superscripted 3 up here tells me that there are 3 zeros in this number. The number that goes out in front is just what you multiply. Here, because the number is behind the decimal, the negative tells me I have 3 zeros in this number, and the actual lead digit in this number is behind the decimal. Now, I wasn't raised in the American system. The Americans do this thing and it's naughty and you shouldn't do it. They don't quote that lead zero. If you don't quote that zero and you say that's 0.001, you're missing the point. If you put the zero in, we now know how to count the correct number of zeros and use the correct scientific notation. So I'm going to urge you all to get into the habit. You're all doing it correctly right now. If you are, fabulous. But if you're not, get into the habit of doing it this way. All right, if I take my milligram and I divide it into 1,000 equal pieces, I now have a microgram, and the micro symbol is not a letter in the English alphabet. It's a letter in the Greek alphabet. That is a mu. It's a bit like a U, but it has a tail that leads in at the beginning. And this microgram is 1,000th of 1,000th. So that is 6 zeros. It's 1/1,000,000th of the original gram. So that is 1 times 10 to the negative 6. And if I take a microgram and I divide it into 1,000 equal pieces, then I get a nanogram. And a nanogram is 1/1000th of a gram. It has 9 zeros if you include the 1 that goes before the decimal point. So it is 1 times 10 to the negative 9. Okay. Imagine for a second we were talking about time. If this is now a second, then 1,000 seconds would be a kilosecond. And 1,000th of a second would be a millisecond. And 1,000th of a millisecond would be a microsecond. And 1,000th of a microsecond would be a nanosecond. This is true for everything. Meters would be the same. If I took a meter and I multiplied it up by 1,000, I would make a kilometer. If I took a meter and I divided it down into 1,000 equal places, I would have a millimeter. And if I took a millimeter and I divided it into 1,000, then I would have a micrometer. Okay, so this system is what we're going to use for all of our numbers, all of our units. And if you're thinking to yourself, hold on a minute, where does the centimeter go? It's in here somewhere. But because it's not a multiple of 1,000, it's actually not one of the ones that we really use. We use millimeters and we use meters. And we stick to the groups of 1,000. Groupings of 1,000 makes things easier because it's consistent across the board. Okay? Okay, so we've seen fundamental units. Let's talk for a second about derived units. Derived units are made up of other smaller units. And that means things like speed. because speed is miles per hour. That is a distance divided by a time. And because we're living in the metric world, in the scientific community, we would never, ever use miles per hour. Our speed or velocity is measured in meters per second. Okay, meters per second. Speed is an example of a rate. A rate is any number divided by time. All rates are something divided by time. And rates are combinations of other units. They are derived units. Volume. Volume is something that describes the amount of space inside a three-dimensional shape. And that shape has a length and a width and a height. And if we take the length and we multiply it by the width and then we multiply it by the height, then we get the volume of that shape. And there is an official Standard Institute's unit in science for volume, and it is the liter. And it turns out that a liter is 1,000 milliliters, and a milliliter is a cubic centimeter. Now, we said we weren't going to use centimeters, and we're not, but it shows that everything is connected. One of the things that we will actually dwell on in chapter 1 is density. Density is mass per volume. And it turns out that the ancient Greeks discovered that pure materials have a characteristic density. That if they had a pure block of iron in this hand and a pure block of gold in that hand, with your eyes closed, you could tell which one was which, because two blocks the same size would weigh different amounts. But the mass per volume was its own characteristic number, and we're going to call that one density. And because that's a chemical indicator of purity, that's something that we're going to spend some time doing calculations on. So we know what units are, and we're getting to the point where we're going to take those measurements and combine them some way, somehow. We have to talk about significant figures, the amount of precision that a number holds. And it turns out that you have to look a little bit closely. It turns out that for significant figures, any number that is not a zero is automatically a significant figure. You count that as being part of the precision of the number. But zeros can be significant under certain circumstances. If there is a zero and it is between two other numbers, then that counts as a digit of precision. And you count them if they are behind the decimal place, but not just exclusively if they're behind the decimal place. They have to be behind the decimal place and after a number. Okay, so I've put some digits on the board. 100, 101, 25,000, 0.0025, 1.0020, and 0.0020. Have a think about how many significant figures there might be in each of these numbers. And then we'll check. Okay, let's revisit these numbers. So when you see a number and you want to count the number of significant figures inside that number, what you really have to do is just look at the zeros, because all the non-zero numbers, they're always going to count. So this 1 counts. These zeros might count if they're between two non-zero numbers. Well, no, they're not between any numbers. And they're after a decimal point. Well, no, they're not. So those zeros don't count. The number 100 has one unit of significant, it has one significant figure. Number 101 has a 1, another 1, and a 0. That 0 in the middle is between two other numbers. So this has 3 significant figures. 25,000 is a 5-digit number, but these zeros, they're not between any other numbers and they're not behind the decimal point. So they don't count. The number 25,000 only has 2 significant figures. What about this one? Does this number look more precise to you than that one? Because it's not. Those zeros don't count because they're not between other numbers, and even though these zeros are after the decimal point, they weren't after the decimal point and behind a number. 1.0020. That number is significant. There are 2 zeros here. Those zeros are between the 1 and the 2, so they count. And then there is a 0 that trails another number after the decimal, so they all count. That number has 5 significant figures. This number, 0.0020, they don't count. The final 0, the trailing 0, is after a real number, and so it counts. So what you do with numbers, it turns out, is slightly different, whether you are multiplying them and dividing them or whether you are adding them and subtracting them. In the case that we are taking numbers and multiplying them together or dividing them, as we're going to do in this particular case right here, your answer is only allowed to have the same number of significant figures as the least number of significant figures that you used in the calculation. So whichever of the numbers in your calculation that has the lowest number of significant figures, that's how many you're allowed to have at the end. Okay, so density. We talked about density. It's characteristic of pure materials. Density is mass divided by volume. So if I gave the class a block of aluminum and said, go away, some of you measure the mass and some of you measure the volume. The team that went away and measured the mass came back and they told me that the block of aluminum had a mass of 54 grams. 2 significant figures, just 2 digits. But the students who measured the volume gave me more precision. They said that the volume of the block of aluminum was 20.02 milliliters. That's 4 significant figures. This number has more precision, but I'm not allowed to carry that forward because the other people didn't do their job right. They only gave me a mass that had 2 significant figures in it. So when I take the top number and I divide it by the bottom number, now my calculator tells me that the answer is 2.697302697.3. Oh, no, 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 no. I'm only allowed 2 significant figures. So I get this. And of course, that 9 makes that 6. really be a 7. So I'm not allowed to quote these numbers. Hopefully now you're seeing that these are very precise numbers. When you're this far down in the decimal, if you were trying to measure that number and publish that number as your own finding, you would have to try really hard. So the fact that the calculator just regurgitated this number to you, that means nothing at all. You're not allowed to use it. Your answer is only allowed to have 2 significant figures, and it turns out that the density of your aluminum block is 2.7 grams per milliliter. When it comes to adding or subtracting numbers and taking significant figures into account in the precision of a number, our rule here is that we're only allowed to keep the precision associated with the least precise number. And so your answer is only allowed to contain the precision of the number used in the calculation that has the least number of decimal places. So in the previous number, I said there were 54 grams of aluminum. If that was actually 2 aluminum blocks, and again, I gave that task to 2 different sets of students, and the first set of students went away and they said that their block of aluminum weighed 27.00025 grams. All of those zeros count as being significant figures. So this is a 1, 2, 3, 4, 5, 6, 7. That's a 7 significant figure number. The other team went away. They used a different balance, perhaps, and they said that they had 27.0 grams. That was the mass of their block. So now when we add these numbers together, I have to set a limit. The limit is the number in my calculation that has the least number of decimal places is right there, 1 decimal place. And so I'm not allowed to have anything in my final answer that is to the right after that decimal. So 27.00025 plus 27.0 comes out that way. That's my answer. Not allowed to have any numbers after this. Always remember, if you don't put the units in, then the number has no meaning at all. Okay, this few minutes is the survival guide for the material in the first week. We'll have more of a conversation during the week. Good luck to you.